Hello everybody, getting ready to do lesson 9.1 part 3 of pre-calculus math today. In today's lesson, 9.1 part 3 has 8 points on your notebook guide, and then 12 points will go into your classwork sheet. Students have those out. Name, date, period. If you're an onliner or a homeschooler, put your due date here. And then let's just jump right into it here. Reflective property of parabolas. A line segment that passes through the focus of a parabola and has endpoints on the parabola is called a focal chord. Not a vocal cord, but a focal chord. The specific focal chord perpendicular to the axis of the parabola is called a latus rectum. Parabolas occur in a wide variety of applications. For instance, a parabolic reflector can be formed by revolving a parabola about its axis. The resulting surface has the property that all incoming rays parallel to the axis are reflected of the parabola. This is the principle behind the construction of parabolic mirrors used in reflecting telescopes. Conversely, the light rays emanating from the focus of a parabolic reflector used in a flashlight are all parallel to one another as shown here. So here's an example here of a parabola. Here is a focus. Presumably this is where your light would be, your light source in a flashlight. A parabolic reflector light is reflected in parallel rays. So because of the parabolic structure here and light, considering the physics of light, you have light rays that go out in a parallel fashion, which makes it a more intense light source. So what about it? A line is tangent to a parabola at a point on the parabola. Here is our tangent line here on your parabola. When the line intersects but does not cross the parabola at the point, so right here, point P. Tangent lines to parabolas have special properties related to the use of parabolas in constructing reflective surfaces. So the reflective property of a parabola, the tangent line to a parabola at point P over here, here's your tangent line, makes equal angles with the following two lines. So here's angle alpha, here's another angle alpha here. We have our focus. So this angle between our focus and P, guess what? I bet, well, let's see. 1, the line passing through P and the focus, which is this line here. And then 2, the axis of the parabola. So here is our axis, here the parabola, and down here we have another angle. Guess what? Guess what? Finding the tangent line at a point on a parabola. So find the equation of the tangent line to the parabola given by y equals x squared at the point 1, 1. So y equals x squared is a pretty basic parabola. Here's our parabola here. And then at point 1, 1, which is here. So here's our tangent line here. For this parabola, P equals 1/4. Here is our focus, and the focus is 0, 1/4. That's our focus, as shown. So you can find the y-intercept 0b, which is down here, of the tangent line by equating the lengths of the two sides of the isosceles triangle shown. So this d1 equals 1/4 minus b. So distance 1, which is here, this distance here is 1/4 minus b. So b would be, see, 1/4. Here's our b. So the distance there would be 1/4 minus b. And then distance 2 here would be the radical 1 minus 0 squared plus 1 minus 1/4 squared would equal 5/4. So our distance of this here, distance 2 would be 5/4, and then this is distance 1 here. So we're going to form like a right triangle here. that's what we did here to use this radical. We used a Pythagorean theorem to find distance 2 here. This is how they get this 5/4 here. Because guess what? We know this distance here is 1, and then we know this distance here is 1 minus 1/4, and then we add those together to get, this is the hypotenuse on this right triangle here. That's how we got 5/4 for D, for the distance of 2, this line segment there. Okay, note that D1 equals 1/4 minus B, so D1, this is our D1 here, is 1/4 minus B rather than B minus 1/4. So the order of subtraction for the distance is important because the distance must be positive. Setting D1 equals D2, otherwise our isosceles triangle, we know that much. This is isosceles here, where we have two sides that are equal, and then this side here is what? So we're still trying to find the length of that side there. To find that length, so 1/4 minus B equals 5/4, we did that one, and then B equals -1, so B, we know this is -1 here. So the slope of the tangent line, to find the slope of this tangent line, we need, so we're going to use another triangle here. Here is our hypotenuse of a right triangle here. So the slope of the tangent line is rise over run. So we have 1 minus and -1, which is 2. So this is 2 here. And then rise over run, our run here is 1. So it's 2/1, which is 2. It's a positive slope. It's rising from left to right. So you know it's positive, right? So in the equation of the tangent line in slope-intercept form, we know the slope is y equals 2x minus 1. Here's our y-intercept down here, which is -1. So we got that. So let's try one here. Find the equation of the tangent line to the parabola at the given point, and find the x-intercept of the line. So x squared equals 2y, and then here is where it's tangent to this parabola. So knowing that, we're going to do this part of this problem, students. You get part 2 to do on your own. So x squared equals 2i, 4, and 8 is our point where it's tangent. So p equals 1/2. In this case here, p equals 1/2. So focus will be 0 and 1/2. So distance of 1 would equal 1/2 minus b. We know that from up here, 1/2 minus b. And then I'm going to let you do the rest of that, students. Let you do that on your own. Technology tip. Try using a graphing calculator to confirm the result of example 7 by graphing. y1 equals x2 and y2 would equal 2x minus 1. So to do that, these lines should intersect at the tangent. In the same viewing window, you should be able to see that the line touches the parabola at point 1, 1 is what that should happen. And that is your part 3 of 9.1, pre-calculus math. Email me for course materials, questions. Thank you.